Hi, this is lecture 23 of M3. In last two sessions, we have seen notion of what we have called as summable sequence A from N to R. This sequence is called summable sequence. For this sequence, we have assigned other sequence that we are calling as SA from N to R. For each n, we are assigning sum of first n elements ai is equal to 1 to n. For this sequence, we assigned this sequence SA, and whenever this sequence is convergent, then we will call this to be summable sequence, and the limit of this sequence we are denoting by this symbol an is equal to 1 to infinity. I have said last two times also, now I am saying again. This is a notation for limit of this sequence, assuming it is convergent. Otherwise, we use this symbol along with something before and after, some phrase that says the series, this thing, converge or diverge, something like that. By that we mean this sequence of partial terms is a convergent or divergent, or whether we are trying to check whether it is convergent or divergent, like that. And then we have seen some example. So one of the example is summation 1 by n. This we have seen it is not convergent. Before that we have seen, we are trying to see whether this makes sense. Then we realized it doesn't make sense for a sequence like this for a sequence an, and for this series to converge, we realized that this sequence should go to 0, but this constant sequence is not going to 0. So that was out of question. Then we were checking 1 by n is a nice example of a sequence that goes to 0. Then we tried to see whether this is convergent or not, this series is convergent or not. Then we realized that's also not convergent. And then we focused on series that are whose terms are non-negative. So we have seen three results that says, suppose we take a series summation an, and every element of this series is non-negative, then this series converge if and only if this sequence, the sequence related to the sequence of partial terms SAN is bounded above. That is the first result that we have seen. Then we mentioned about something called the comparison test. What is it? Suppose I have a series an, and suppose every an is a non-negative, then to prove this is convergent or divergent, one can use other series whose convergence or divergence we already know, and this is all non-negative. That's what is comparison test. Then we mentioned about something called so then we realized for series with non-negative terms we seem to have enough machinery to handle them. So then we realized it may be useful to convert every series into series of non-negative terms. That way we end up with the notion of mod an 1 to infinity. A series for which this series is convergent is called absolutely convergent series. Then we said that a series which is convergent, just this, but this is not convergent, is called conditionally convergent series. Then we have said that this series minus 1 power n by n is conditionally convergent. All this we have seen. Now before proceeding further, and I have mentioned about some other results also. So before proceeding to more results, let us do one more example. So again we were looking for series that is convergent. So we are looking for some examples of series that are convergent. So for that to make sense, we need to have a series. Start with the series. This goes to 0. As I said, we mentioned about this series 1 by n, summation 1 by n. This goes to 0, but this series was not convergent. So as the next step, we took something like summation L power n, where L is a positive number which is less than 1. So this we have seen to be convergent, and this limit was L by 1 by 1 minus L. I think that is correct, maybe some, I think that is correct. Now we will take one more example of series, so that this an goes to 0. So one such series is summation 1 by n factorial, n is equal to 1 to infinity. Let us check if this is convergent or not. So if you look in the previous situation, we have seen some result, okay. So now we are trying to see whether this is convergent or not. Now we will use the same idea that I mentioned before. This series summation 1 by n factorial is a series of non-negative terms. So it is sufficient to know that the series of partial sums is bounded above. If you know this much for this series, then we are done. This means this series is convergent. Why? As I said, this is a series of partial sums, series of non-negative terms. So for this to converge, this thing is sufficient. So now the first thing to do is let us check whether the sequence of partial sums SCAN is bounded above or not. So what is SCA1? SCA1 is just 1. SCA2 is 1 plus 1 by 2 factorial. SCA3 is 1 plus 1 by 2 factorial plus 1 by 3 factorial, that is all. SCA4 is 1 plus 1 by 2 factorial, 1 by 3 factorial plus 1 by 4 factorial, and so on. Now we are trying to see whether this sequence SCAN is bounded above or not. Above, or let me write down clearly. So we are trying to estimate each element of this sequence by some other sequence or just one number. That's what we are trying to see. Now observe the following, that see, whenever we are trying to see that summation L power n is equal to 1 to infinity. So this we know to be convergent. So let us try to compare this series of partial sums with the partial sums associated to this series when L is equal to 1 by 2. I mean, how can anybody make such kind of guess? That you will see soon. Observe the following, that 3 factorial is a 3 times 2 times 1. So we are trying to estimate this thing with the third term of partial associated to this series. So this, observe that this is greater than or equal to 2 times 1, that is 2 square, and 4 factorial is a 4, 3, 2, 1. Again I am keeping 2 as reference point. One can try with 3, 4, anything. 1 by 2 is the first choice that I can think of, a number less than 1. One can do the same thing for 3, 4 and so on. Then we have to make some other change. Then we should not be starting at this point, we should be starting at 4. Once we finish this idea, then you will understand what is happening here. So all these terms are greater than or equal to 2. So I am just writing that. So that's equal to 2 cube. In general, n factorial is greater than or equal to 2 power n minus 1 for every n belongs to at least from 3. For n is equal to 2, this is 2 factorial, that is 2, n is equal to 2, this 2 minus 1 is 2, so this is fine. For n is equal to 1, 1 factorial is 1, 1 minus 1 is 0, 2 power 0 is 1, so that's also okay. So we can actually write n belongs to n, but that's okay, no problem. Now what? Observe that 1 by 2 factorial plus 1 by 3 factorial, 3 factorial is greater than or equal to 2 square. So 1 by 3 factorial is less than or equal to 1 by 2 square. So let us write that. So this I am leaving as it is, that is equal to 1, less than or equal to 1, plus 1 by 2 factorial plus 1 by 2 square. 2 factorial is just simply 2. So we have this. Now let us look at the fourth term, 1 by 2 factorial, 1 by 3 factorial, 1 by 4 factorial. That is less than or equal to 1 by 2, 1 by 2 square, 1 by 2 cube. If you observe, that I have already mentioned. For L less than 1, L positive, 0 less than L less than 1, we have said summation L power n is equal to 1 to infinity is convergent. The limit is 1 by not L by 1 minus L. Let me write down this. Limit is L by 1 minus L. Here we have seen one result. What is it? 1 plus L plus so on plus L power n is equal to 1 minus L power n plus 1 by 1 minus L. This is what we have seen. Now we have same thing here also. L is less than 1, 1 L, L square, L cube. This is true for general n. So what we have is S A n is less than or equal to what do we have? The nth term is, yeah, here the fourth term, this is what S4 is, right? S4, for S4 we have only 3 here. So if this is 3, this is 3 less than 4, so that is fine, less than or equal to 1 minus 1 by 2 power n plus 1 by 1 minus 1 by 2. And we have already seen that this series is convergent to L by 1 by L. Again this is of positive terms, this is convergent. That means what? This sequence is bounded above. So in particular this sequence is bounded above. So what we have seen now is using the bounded nature of this bounded nature of sequence associated to this series, we have concluded that that partial sum sequence associated to this series, where is it, 1 by n factorial, that is bounded above. As every term here is non-negative, that is already increasing. So just bounded above implies this is convergent. Now the question is whether it is, now the question is what is the number to which this converges. So this we will see maybe in the later part of the course. You might already know what is this number n is equal to 1 to infinity. This is related to something like E. I am not very sure whether it is E or E plus 1 or E minus 1, but we will see more details. This is somewhat related to E. The reason why I am not saying anything specific here is, for me exponential is a function from some subset of R to some subset of R. So just looking at one element, one image of one element is not sufficient for me. So there anyways we'll write more details about that. This is just a starting point, but keep in mind that this is related to exponential of some element. Now, yeah, so this is one example that I wanted to do. Now again let us go back to the results about sequence of, result about limits of some sequences, and let us try to imitate the same thing here. So in midsum I asked one question, what is it? Suppose an is a sequence of real numbers such that mod an plus 1 by mod an goes to half, then I asked you to check that an is converging to 0. This question I asked. I am assuming you have seen this question in the mid semester at least, and then I also mentioned the solutions. This much is clear at least. So for given sequence, if mod n plus 1 n by mod n is going to half, then an goes to 0. Now that time we did not know about series, now we know about series. So whenever we see some sequence that goes to 0, the first thing to ask is, does it imply, or do we know for such kind of sequences with just this, for such kind of sequences the summation an, or let me write down this, summation an n is equal to 1 to infinity, is it convergent? This is what we should ask. Maybe I will just quickly write down the proof for this. Mod an plus 1 by an is going to half. Why would that imply? An goes to 0. Then once I know that an goes to 0, the next question to ask is whether this is convergent or not. That is the next point, next step. Okay, let us first see this, then we will try to proceed here. So what does it mean to say this goes to half? Whenever epsilon positive is given, then I know it belongs to n exists such that for every n greater than or equal to n, what we have is, see, I do not want to write down modulus every time. So I am assuming that the series is non-negative, that an is a positive always, otherwise you need to put mod, which I do not want to do. Maybe if I allow an to be arbitrary, we have to put mod, then you might have to make some small, very small changes or no changes at all, but the ideas will be same. So I am assuming an is a non-negative, then what happens, an plus 1 by an minus half is less than epsilon for every n greater than or equal to n. Now let me just rewrite this. What is this? This is an plus 1 by an minus half is less than epsilon, minus epsilon is less than the, I am assuming that or an plus 1 by an is less than epsilon plus half. This thing I am ignoring, it is not relevant for me. Now what do we have? An plus 1 by an is less than epsilon plus 1 by 2 times an. This is true for every n greater than or equal to n. In particular, when this n equal to n, this should be true. So I am replacing this n by n. Then I know this should not be there. So we have n plus 1 less than epsilon plus 1 by 2 times n. Just pushing this here. Now in particular I should replace this also, this n also. Right? In particular this is the case. Now let us look at an plus 2. An plus 2 from here, this is true for every n greater than or equal to n. In particular, when n is equal to capital N plus 1, this should be true. So think of this n as n plus 1, then this n will go here, and we will still have the same thing, n plus 2 less than epsilon plus 1 by 2 times an plus 1. Right? This is not this is straightforward. I am replacing n with n plus 1. So n plus 1 plus 1 is n plus 2. This is going here, that is what I am writing here. But we already know some estimate for an plus 1. What is this? Epsilon plus 1 by 2 times an. So again we will write down again same thing, epsilon plus 1 by 2. This is coming from this thing. Now for this thing also there is 1 epsilon plus 1 by 2. Let us write down that also, epsilon 1 by 2 times an. So I do not write 2 times, so I will just write square, just the square, and I am just pulling it here. Now in general I think you can guess what is happening here. For general k, an plus k is less than epsilon plus 1 by 2 power k times an for every k greater than or equal to 1. Right, this is starting, this inequality is starting at an plus 1, this point being an plus 1. Now see, epsilon can be any positive element. In particular, epsilon can be 1 by 4. What is special to 1 by 4? There is really nothing special. I took 1 by 4, so that 1 by 4 plus half is still less than 1. Epsilon is equal to 1 by 4, epsilon plus half is equal to 3 by 4. This power k is equal to this power k. Here there is a k which is not very clear here, so let me write down again. But you already know, I mentioned just now, for any number L less than 1 positive, L power n goes to 0. So 3 by 4 power k goes to 0 as k goes to infinity. So this sequence in k is going to 0. Now what? This implies this sequence is going to 0. Why? On the left hand side we have a sequence that is still positive, 0 less than or equal to this. Then we have said that this is a fixed number, n is fixed, and this sequence is going to 0. So this thing is going to 0, the whole thing is going to 0, this is just a constant. So again the squeezing theorem says there is a 0 here on the left side, on the most left side. On the right side we have a sequence in k that is going to 0, as k goes to 0, that says this sequence should go to 0, a n plus k should go to 0. See, this does not say, or it is not very clear whether this is same thing as saying a n going to 0, because this sequence starts at a n plus 1, a n plus 2, so on, this sequence is going to 0, but you already know and I already said also, if I have a sequence and if I have a sequence, we are looking for the convergence of that sequence, all we know is after certain stage that is convergent going to something, then the same thing can be said about the sequence starting at a1, a2 dot 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 an plus 1, so on, this also goes to 0. I said before also. So if I know a subsequence starting at some point, this is not any general sequence, we are ignoring, okay, let us discuss this last one phrase. So if I know that for a given sequence a n, ignoring first, here we are ignoring the first n terms, ignoring n terms, the rest of the sequence is convergent, converging to 0, then the whole sequence is convergent, converging to 0. So this says a n goes to 0. So all we have used here is this phrase, this element can be made less than 1. This is possible only because this element is less than 1. Suppose let us epsilon plus 100, can we make this to be less than 1 for any epsilon positive? Not possible. 100 is too much maybe, let us take 10. Can I make epsilon to be epsilon plus 10 to be less than 1 for any epsilon positive? Not possible. And one can keep on trying, then realize that for epsilon plus say delta to be less than 1, it is necessary that delta to be less than 1. Even if delta is equal to 1, this still does not hold. And whenever delta is less than 1, one can of course find epsilon positive such that epsilon plus delta is less than 1. How do we know that? Delta is less than 1, so 1 minus delta is positive. So one can of course see there is 0 here, 1 minus delta here, so there are enough gap here, so one can just fix some random epsilon positive. Or one can of course take 1 minus delta by 2 for any positive number by 2, we will land somewhere here. So that is one choice. So let me write down that. So for any L less than 1, 1 minus L by 2, epsilon is equal to 1 minus L by 2, will make epsilon plus L to be less than 1. How do I know that? Let us try that. 1 minus L by 2 plus L. What is this? 1 minus L plus 2L by 2. This is how much? 1 plus L by 2. Is it less than 1 already? Yes. Why? 1 plus L. Suppose for this to be true, we need to have 1 plus L less than 2. This is same thing as saying L less than 1. So just back trace. L less than 1 implies 1 plus L less than 2 implies 1 plus L by 2 less than 1 implies this thing is a less than 1 implies this thing is less than 1. So this is really necessary that whatever L I am choosing here, this element should be less than 1, only then I can make this element to be less than 1. Whenever I know this is less than 1, this power is going to 0, that is the strategy. So maybe one can generalize this to the following statement. Suppose this goes to L and L is less than 1, of course positive, because even if n is non-negative, if n is also negative, we are putting mod anyways. So this cannot go to negative element. If n is non-negative, this can never go to negative element. So 0 is less than 1, it is understood, but still we can write down. Let us write down 0 less than L less than 1. Suppose we have sequence an non-negative, this fraction goes to L 0 less than L less than 1, then an goes to 0. Now the next thing to do is check if this thing is convergent or not. That is the idea. So now what I have is, let us try to use this idea, use this observation, not the idea, this observation. And what is it? Let me write down that one more time. A n plus k is less than epsilon plus 1 by 2, that is what I have written before, but okay, one can replace this whole thing by L again. The epsilon plus 1 by 2 power k times a n, right. Now what? This whole thing implies summation a n plus k is equal to 1 to infinity. This is convergent. Why? This thing, this candidate is less than 1. So series associated to this fraction, this element is convergent. So what we have is summation epsilon plus 1 by 2 power k is equal to 1 to infinity is convergent. Why? We have some element L that is less than 1, right. Of course you can choose epsilon to be something whatever I have done before. So this element is less than 1, so positive, so that element power k, this series is convergent. Now this is just one number, any real number, so this also should be convergent, right. So that is what the sequence of partial sums associated to this series is bounded above. Again, this less than or equal to this implies for this series sequence of partial sums associated to this series is less than or equal to sequence of partial sums associated to this series. So the sequence of partial sums associated to this series is bounded above, and all these are non-negative. So this non-negativity and this thing implies summation k is equal to 1 to infinity a n plus k is convergent. Now does it say anything about the whole series summation a n is equal to 1 to infinity? Yes, whatever I have said in the last session. Suppose we have a series something like this, and this implies summation n is equal to say capital N plus 1 to infinity a n is convergent, and we have this result is equal to a1 dot 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 plus a n plus summation n is equal to n plus 1 to infinity a n. So whenever I know that after a certain stage in the series, if I ignore the first few elements in the series, if I know the resulting series is convergent, then this combination is convergent. So here we know after n plus 1 the corresponding series is convergent. So even if you add the first n elements a1 plus a2 plus so on plus an, that plus this is the limit of this series. So this series converges, and this is equal to a1 plus a2 plus an plus this. So what does this say? This says, suppose I have a sequence of non-negative terms such that an plus 1 by an is going to L, then an goes to 0. That is that's what I have seen long back. And this is not just this. What we know is summation n is equal to 1 to infinity is convergent. So this result, which was very easy to understand, is called ratio test. As I said before, the only thing that again I forgot to mention here, L is less than 1, 0 less than L less than 1. Only because L is less than 1, you were able to realize that n is going to 0. Where is it? Yeah, n is going to 0. Then only because L is less than 1, and because of this comparison, we realized that this series with excluding an is convergent. Then we involve an here also, so the corresponding series is convergent. Then this thing says the sequence of partial sums associated to this series, each term is less than or equal to sequence of partial sums associated to this series. again this series convergent, every element is non-negative, so the sequence of partial is bounded above. That implies this series, the sequence of partial associated to this series is bounded above. So combining all those results, we realize that this series is convergent, the series starting at n plus 1. Then we know, last time we said that if I take a series summation 1 to infinity a n, if I know, excluding the first n terms, if I know that this series is convergent, then this series is convergent. But the limit will be different. Limit is a1 plus so on an plus this is equal to this, and that's what I have written here, nothing more than that. Okay, this test can be used to conclude convergence of series of non-negative terms. See, again, just like in the previous case, one can of course do the following smart trick. You take any series an is equal to 1 to infinity, and don't assume, you don't have to, an need not be non-negative, but one can consider this series, right, n is equal to 1 to infinity mod an. Maybe for this series you can apply ratio test, every element is non-negative. Suppose for this series you get that L is less than 1, that where is it, this fraction is going to L and L is less than 1, then you can apply this idea of ratio test to this series summation mod an. What does this say? This says this thing, the series without any mod is absolutely convergent. Then you know, I said in the last session, absolute convergence implies convergence, that says this is convergent. So here one need to keep the following thing in mind. So even if I know that an plus 1 by an is going to 1, that means L is equal to 1, one cannot apply the trick here, because if I take this thing is equal to 1 power k, that is not convergent, 1 power k is just 1, we know this series is not convergent, so one cannot apply that idea, so that is the problem. So only when I know that this fraction n plus 1 by an, this ratio is going to L is less than 1, only then I can apply this ratio test to conclude about convergence of this. Again, as I said, one can apply the ratio test for arbitrary series also, but it's not straightforward. This step should come in between. Firstly, we should consider the corresponding series of non-negative terms, this mod an thing, apply the test for this. It may not work, I mean it may converge to 1 or it may converge to 2, it may not converge at all, that is that. Suppose it is convergent, suppose you get some positive result from this, then this thing will follow. Why? Absolute convergence implies convergence, so just checking for this is sufficient. So this may be one reason why in many textbook people in general, people write down test only for series of non-negative terms, because suppose we are checking for convergence of this, and one obvious thing to do is consider corresponding series with mod an, and this is series of non-negative terms. Suppose we can apply the test for this, and this became positive. If it is negative, then we cannot do anything, we cannot really conclude anything. But if this is positive, suppose we get that this is convergent, then this holds. Why I am saying this? Suppose it is negative, we cannot say anything about this. What does it mean that this is negative? This means summation n is equal to 1 to infinity mod an is not convergent. So suppose we get that kind of result, negative result, then we cannot say that this is not convergent. Why? We have examples of series minus 1 power n by n. I already mentioned this, but I am mentioning again. We have examples of series for which modulus does not converge, but this series converges. What is the modulus of this? Just 1 by n. This series with 1 by n does not converge, but this series with minus 1 power n converge. So this 2 here is useful only when we get some positive result here. This is convergent, one can conclude that this is convergent. That is the idea. So this is called ratio test. One can try to prove that some series is convergent using this, but getting limit is a different question. We are only checking whether some series is convergent or not. Looking for limit may be done in, maybe it takes some time. So let us try with some example. So consider the following series. We checked that see 1 by n was converging to 0, but we realized summation 1 by n is equal to 1 to infinity is not convergent. Then I said I am afraid to check for 1 by n square, 1 by n cube and so on, even though everything is converging to 0. Now I have enough confidence to check. I am not saying this is positive or negative. I have enough confidence to check convergence of this. One result is this: one can apply the ratio test. It may not give anything, but you can simply apply and see what happens. So consider the following series: summation n is equal to 1 to infinity 1 by n square. Let us check if this series is convergent or not. First thing to check is what? Every element of this series is non-negative. Is it non-negative for this series? Yes, it is 1 by n square, n belongs to n. So this is non-negative. Now what we need to check? an plus 1 by an. What is this? 1 by n plus 1 square by 1 by n square. What is this? N square by n plus 1 square. Now what do we have? N square by n square plus 2n plus 1. Again sorry, maybe we need to push this again to this. So what we have is 1 by n square plus 2n plus 1 by n square. What is this? 1 by 1 plus 2n plus 1 by n square, or maybe we can write down this also 2 by n plus 1 by n square. Okay, so now what? 2 by n goes to 1, 1 by n, 2 by n goes to 0, 2 by n goes to 0, 1 by n square goes to 0, so this whole thing goes to 1. So this series goes to 1. So now there seems to be some problem. For 1 by n square also we got the same thing, that is going to 1. So we cannot really use that result, that ratio test. So summation 1 by n square 1 to infinity. Convergence is not very clear. We cannot proceed further using ratio test. That's what we mean. So this suggests that maybe we need to have other ways to check the convergence of some series. Now one more see the same idea, that given a series, given a sequence an such that mod an plus 1 by an goes to L, L is less than 1, then an goes to 0. Do the same thing. Now instead of taking this ratio, one can take the root also. For that also we will get the same thing. Let me show that. So now what we have is, let us take a series of non-negative terms. Consider the following series: an power 1 by n. Suppose this goes to L. Then I am claiming that an goes to 0. I mean the trick is same trick. Whatever we have used for ratio, we are using same thing for this also. How do we know that? Let us do the following. So again epsilon positive, there is n belongs to n, such that whenever n is greater than or equal to n, what we have is an power 1 by n minus L is less than epsilon. So this is what? an 1 by n minus L less than epsilon. This part I am not writing. So this is same thing as saying an power 1 by n less than epsilon plus L. I am just taking nth power on both sides. This gives what? An is less than epsilon plus L power n. This is more straightforward than the previous thing. If L is less than 1, then I said I can choose epsilon positive such that this thing is less than 1. Anything less than 1 goes to 0. An is already greater than or equal to 0. So 0 less than or equal to this. So again using the same squeezing theorem, here it is straightforward. I mean after some n it goes to 0, the same thing, but here it is more easier to handle or easier to conclude than the previous ratio testing. So again this thing is true for every n greater than or equal to n. This sequence goes to 0. So the sequence an plus 1, an plus 2, this whole thing, this sequence is going to 0. Again, even if we have some elements in between before that, it should not affect the convergence and not the limit also. So this is what, if I know that for non-negative terms, the series of sequence of non-negative terms, if this thing is going to L, then n goes to 0. Again the same thing we should ask, do I know that for such kind of sequences, the series whether it is convergent or not, n is equal to 1 to infinity, is it convergent? It may be boring for you because I am doing the same thing that I have done before, but people give different name for those two, so I have to do. So what we have is the following, an is less than epsilon plus L power n. Now if I take this is true for every n greater than or equal to n. So if I take the corresponding sequence of partial sums, that also we have the same thing, yes an less than I do not know what to call this, let me call this T n epsilon L, something like that, for every n greater than or equal to n. This is sequence of partial sums associated to this series. Let me write down that also, summation epsilon plus L power n is equal to 1 to infinity. But here we can talk only about n that is greater than or equal to n. So in particular this is also true, let me write down that also, Rn plus 1, whatever it is, n only actually, not n plus 1. Now this is convergent, which means what, the sequence of partial sums associated to this series is bounded above, because everything is non-negative. For this series to converge, the partial sum sequence should be bounded above. So this is bounded above, this is 0 less than SAN less than that. So this implies this sequence is bounded above. So this is bounded above sequence of non-negative terms, increasing sequence. So this is convergent. This says what, summation n is equal to n to infinity Rn plus 1. I lost the track, is that it is Rn plus 1. In any case n plus 1 only, no, n, sorry, we need to put an here, but that is okay, just one element, should not change the limit for sequence convergence. Here it makes a difference, I need to add here an or n plus 1 depending on where I am starting with. So here we know that this thing is convergent, this series is convergent. Now all I need to do is, I need to just add a few elements and then I will get summation n is equal to 1 to infinity. So this is what, suppose I have a series summation an 1 to infinity such that this root, previously it was ratio, this root, nth root is going to some element that is less than 1, 0 less than L less than 1, then this is true, there is no surprise, and this is convergent, no surprise for this also. This is called root test, no guess, no prizes for guessing the name, that is clear. But if some of you thinking that these two are really same thing, why they are giving different names, you are in a good company, I am also thinking the same thing, that these two results are really the same idea. I do not know why they have to be with different names, right. Only the same trick I am using. Suppose I have some number L less than 1 and some series is going to, some sequence is going to that, and then I can do some small changes and then conclude that it is going to 0, the sequence going to 0. Then when some sequence goes to 0, then I know that whenever something goes to 0, the first thing that I want to do is I want to check the convergence of this corresponding series. So that I will do, and it worked. So now I have three tests: comparison, ratio and root. And any other test that you can find in Indian textbook, it is just some small changes here and there for these maybe the same idea. So you should not feel uncomfortable when you see 15 tests mentioned in the textbook. No, 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 all those are just some smart tricks, not really that smart. See this, whatever I have done here, this is not very difficult, right? This is very straightforward. Whatever this sequence going to 0, that was the first step. This was the reason why I have given not this question, the previous question. Where is it? Yeah, this question I have given in the mid semester exam. The only one that I gave in the mid semester exam is to give you that was a hint that this thing we are using in later part of the course. That was the only purpose of giving that in the exam. Yeah. Now what? Let us check the convergence of some series using ratio test, root test. Ratio we have already done. Let us see, using ratio test we cannot conclude anything about this, right? So let us see whether we can say anything about this convergence using ratio test. What we need to do is, for each n we have to consider the following: n square power 1 by n. Where does it converge to? Okay. Now I am leaving it to you to check that this sequence is going to 1. So even with the ratio test, we could not find anything. From root test also we could not really find anything about the convergence. This is going to 1, so we cannot apply that same idea before. So now we know 2 tests. I mean, with those 2 tests we could not really proceed further. And comparison test, the only thing that I can relate that with is the following: n square is greater than or equal to n, and n square 1 by n square is less than or equal to 1 by n. But this series is 1 by n is not convergent, so I cannot use that idea to conclude the convergence of this. So with 3 tests we cannot really say anything about the convergence of this. So maybe there are other tests that checks the convergence of this. Let us do this from basic principles. What is it? Again same thing. For what did we do for 1 by n factorial? Suppose I know that this sequence of polynomials is bounded above, then we are done, because every element is non-negative. Once I know that this thing is bounded above, that implies this series is convergent. So I need to check the following. What I need to do is 1 plus 1 by 2 square something, 1 plus 1 by 2 square, 1 by 3 square something. This something should be same, it should not be different depending on the n I am choosing. So we need to have SAN less than or equal to some number for every n belongs to n. That is the strategy. Now how do we proceed further? Now observe the following: n square is greater than or equal to n, that is fine, but this was not useful. This implies 1 by n square is less than or equal to 1, summation 1 by n is not convergent, so we cannot really conclude anything. Let us change the starting point. See, n square is greater than or equal to n square minus n. This is what I am considering. This looks as a surprise. It's not very clear why I am considering this. You will see soon. This implies what? 1 by n square is less than or equal to 1 by n square minus n. 1 by n square less than or equal to 1 by n square minus n. That is same thing as n times n minus 1. See, 1 by n was not very useful for us. So now we are splitting into 2 parts, n times n minus 1. So and these 2 combine to give this. So that is the reason why we are doing that. And we are hoping that taking 2 portions from divergence series combinedly is giving a convergence series. That was the idea. It may not work. We are not very sure about that, but let us try. So this thing we are writing as 1 by n minus 1 by n minus 1, right? N minus 1 minus n is just minus 1, so this is maybe plus. So what is this? Let me just check quickly. N times n minus 1 times n minus n plus 1. Yeah, that is correct. Okay, so we have this. So 1 by n square is less than or equal to this. Now let us do the following. Let us check 1 plus 1 by 2 square plus 1 by 3 square. This is less than or equal to 1 plus 1 by 2 square. I am writing as less than or equal to 2 minus 1 is 1. So 1 minus 1 by 2. For n is equal to 2, I am writing this. For n is equal to 3, I should write minus 1 by 3 plus n is equal to 3 is what? 3 minus 1 is 2, so this is 1 by 2. So at this stage, observe the following, that these two gets cancelled out. Let us try for 4 also. What is the hurry? Let us do very slowly. For 4 square, what we have is 1 by 4 minus 1 is 3. So 1 by 3 minus 1 by 4. Now at the fourth step, what we have is this is already gone in the last step itself. Now this is also gone. So at each step, whatever is coming in the previous step, that extra term is going. So more generally, what we have is the following: SAN, the one this means the partial sum substituted to this series 1 by n square is less than or equal to, I have these two I cannot do anything, they are very strong, 2 minus 1 by n, right, this one. So this is true for every n greater than or equal to n, for every n belongs to n. There is no special element from where it is happening. This is true for every n. Now what we have is the following: this element is always less than 2 because minus 1 by n is negative. So this whole thing is less than 2. Now what we have realized that we have a sequence of partial sums associated to the series 1 by n square is bounded above. This is true for every n belongs to n. What does it say? Again the same basic principle says, suppose I have a series of non-negative terms such that every element, such that the sequence of partial sums is bounded above, then this is convergent. The same thing we have seen, summation 1 by n square n is equal to 1 to infinity is such that for this series the partial sum sequence is bounded above by 2. So this series is convergent. What does this say? This says two things. First thing is the following, that check this ratio test whatever I have done. For the ratio test, where is it? Yeah, for the ratio test. So for this we have checked, it is going to this is going to 1. So if the limit is going to 1, there are two possibilities. See, even though this is convergent, now we know it is convergent. For convergence, limit is going to 1. Let us check for 1 by n, summation 1 by n. What about n plus 1 by n? This is 1 plus 1 by n, this is going to 1. So ratio test is not so nice in the sense when the limit is going to 1, there is example of convergence series, there is example of divergence series. So that is not really a nice thing to happen. So when it is going to 1, we cannot really say anything because there are two examples. 1 by n square, ratio test is giving ratio test is saying that the corresponding limit for the an plus 1 by an is 1. For this also it is 1. So there are two series, one is convergent, one is divergent, such that the corresponding ratio test is giving same limit as 1. So 1 is not, if the limit is 1, we cannot really use it, we cannot really conclude anything. There are two things happen. Same thing with the root test also, that for both convergent and divergent series, I mean, we have an example when L is equal to 1, there is a convergence series and there is a divergence series. Further, you need to know that nth root of n is going to 1. This I am leaving as an exercise. Check for yourself. I think you know enough sequence of real numbers to check that. I will add one more test in the lecture notes. One more test I will add when we deal with integration. that's I cannot add it now, because that needs to, for that you need to know some integration theory. Okay, so that's all for this session. In the next session we will do something called power series. Then there is something called rearrangement of series that we will do. Then we'll see some examples. One test that I am going to add in the lecture notes. For that I will say something about that test. Then we will do some examples of checking convergence of series. That's all for with that we will conclude about series of convergence of series. That's all.